Hey guys, welcome to the third session on probability. So we'll be again looking at a quick recap here. Then we'll be going through a couple of basic concepts. So these would be the last concepts from the probability theory. And then again, we'll be moving towards more interesting stuff. We'll be looking at a couple of questions on expected value calculations, which are based on probability theory as well. So looking back, we saw how the probability is defined as the likelihood of a particular event to occur, on the basis of which we saw that the probability values can only range in the value of 0 to 1, since 0 means that that particular event will never occur and 1 means that it will always occur. Then the second property we saw was the sum of probabilities of all the outcomes of a particular random experiment is always 1. So this was the second property. Then we look at what are mutually exclusive events. So these are the events which cannot happen together, and therefore the probability of occurrence of both of these events together is always equal to 0. Then we looked at the addition rule of probability. This is nothing but the probability of union of two events. By union, I means the OR operator, which means at least one of the events have to occur. Either exactly one of them occurs or both of them occurs. So all those cases are included in the union operator here. This is computed as the sum of individual probabilities of those events, and we subtract the intersection probability of the two events from this particular sum. The intersection is nothing but the AND operator, which means the probability of both the events to occur. Next, we look at what are independent events, where the occurrence of one event doesn't affect the probability of occurrence of the other events, and therefore the probability of A given that B has occurred is still probability of A, and the probability of B given that A has occurred still remains the probability of occurrence of B. Then, based on the independent events only, we looked at the product rule of probability, which is nothing but the intersection probability for the two events is the product of individual probabilities. Note that this particular product rule is only valid for independent events. Next, we looked through a couple of examples in our previous session on what is conditional probability and how it is computed. So if you remember, we looked at the ball example, red and blue colored balls with two draws. Apart from that, we looked at this classroom example where we looked at the number of students in each of these three classes A, B and C. And then we also looked at another variable, which is the gender of the student in each of these classes. So we looked at the number of males and number of females in each of the three classes here, based on which we calculated different kinds of probabilities. The first one we looked at was the conditional probability, the probability of the student being male, given that he was selected from the classroom B. So this was computed as nothing but total number of males from who are from class B and divided by the total number of students from B, and this was later computed to be 15 by 30, since there are 15 males in class B and there are total 30 students in class B, which came out to be 1 by 2. Now next we calculated the joint probability, which is the P probability of M intersection B, which means the probability of getting a student who is both male and is selected from class B. So this was again computed as the total number of students who are male and selected from B divided by the total number of students across all the sections. So this was computed as 15 by 90 here. So the only difference between the condition and the joint probability here is that in joint probability, we'll have to take the total sample size across all the classes here, since we are not given the condition that the student is getting selected from only class B here. Next, we looked at the marginal probability of the student being a male student. So for this, we looked at the total number of male students. So this is number of male students divided by the number of total students, which was again calculated to be 45 by 90. And similarly, the probability of a student being selected from class B was calculated as 1 by 3, since there are equal number of students in each of the three classes. Now, moving ahead, we wanted to mention something regarding the conditional probability itself. So again, using the same example, we saw this particular formula here to calculate the conditional probability. The condition given here is that the student is selected from class B, and therefore the total number of students from class B is taken in the denominator in this particular case to calculate this particular probability. Now, if we write it in let's say a set form, we have number of students who are both male and from class B, and we are dividing it by total number of students from class B. Now let us say we divide the numerator as well as denominator with the total number of students across all the classes. So let's call it T. So this particular value is actually T here, or you can say NT, the total number of students, and we then divide it by the total number of students in class B with total number of students across all sections. So we are just dividing both the numerator and denominator with this 90 value here, and therefore the value should still remain the same. Now if one notices here, the numerator has actually become the probability of getting a male student as well as a student who is from classroom B, and the denominator is nothing but the marginal probability of getting a student from class B. So we have come up, in a way, we have derived a particular formula here, which is nothing but Pm given condition B is Pm intersection B divided by Pb. So this is very intuitive as well. Since we are given the condition here that the student is getting selected from class B, therefore this probability is totally taken in the denominator here, because we are actually computing the part of this probability of getting getting a student from class B and who is male also. So therefore we put both the conditions in the numerator here, but the condition which is given, that the student is already selected from class B, we put that in the denominator here. Now this particular formula is actually a very famous formula which will be used a lot in most of the or in many of the machine learning algorithms, and this is nothing but this is called Bayes formula for conditional probability. Since the LHS here is actually a conditional probability, therefore this is Bayes formula for conditional probability. Now another thing to note from this is, let us revise the product rule now. So if we just cross multiply this here, we get Pm intersection B is nothing but Pm condition B multiplied by Pb. So this is nothing but a generalized product rule. So earlier we saw the product rule only for the independent events. Now we have a generalized product rule. So let's call it a generalized product rule of probability. Now let us say we want to derive back this particular formula for independent events. So let us say we want to have it for independent events. Now let us say M and B are independent, although they might not be in our particular example, but let us assume they are independent. Then we know that Pm given B is Pm, since the occurrence of B doesn't affect the probability for B, and therefore we again get back our old formula, which is the intersection of the two events is nothing but the product of individual probabilities of the two events to occur. So here we have now got the generalized product rule of probability instead of just having the product rule for the independent events which we have seen earlier. Okay, so this is regarding the generalized product rule of probability. Now one last thing which we wanted to look in this particular session is law of total probability. So we call this law of total probability. Now let us say, again using the same example, so let us shift this particular thing. Now let us say we again look at the same example here. We try to derive the law of total probability from this particular example. Now let us say we have to calculate the probability of getting a male. So this is nothing but a marginal probability, since we are not considering the second variable, we are only considering the first variable. Now this can be calculated as the probability of getting a male who is also in class A plus the probability of getting a male who is also in class B plus the probability of getting a male who is also in class C. So these are the only three possibilities in which we can get a male student. Either he is from class A or from class B or from class C. Now from our previous product rule which we just derived, we know that P M intersection B. So we are using this particular rule which we just derived. This is nothing but PM. So since we are using the generalized rule here, PM condition B multiplied by PB. Now if we use this product rule, the generalized product rule, on all of these three terms here, we would be getting the law of total probability here actually. So we can just write the terms here. So once again, there are three classes here, therefore we have three terms here. Now this can be written as, in a more generalized way, PM is nothing but, let us say this particular variable, let us say is X variable. So we'll write I belongs to X and we have probability of getting an M from I multiplied by PI. So what this summation does here is, it is only adding up all the possible values of X here, which is the class. So X here is the class variable. We are considering all the possible values of this class, which is considered in this particular probability of getting a particular class. So this is again a marginal probability. And this is the conditional probability of getting a male student given that a student is selected from the class I here. So this is the law of total probability, and now we can easily apply it to get the required probability of getting the male student here. So let us say now the probability of getting a male from the class A is nothing but 10 upon 30, since there are 30 students in class A and 10 of them are male. And similarly, the probability of getting a male student is 1 by 3. So the probability of getting not a male student, sorry, this is actually equal to PA. So we know that PA is equal to PB. So all these three terms here are equal, since we have equal number of students in each class. So all these three terms are equal to 1 by 3. Now the probability of getting a male from B is again like we have calculated before, it's 15 by 30. So this is again multiplied by 1 by 3 plus, to get the probability for C now we have 20 by 30, and this is again multiplied by 1 by 3. Now we take 1 by 3 common here, and in bracket we get 10 by 30 plus 15 by 30 plus 20 by 30, which is nothing but 45 by 30, and we get the required probability of 1 by 2, which is again the correct probability, since we know that out of the total 90 students here, 45 of them are male. Therefore this is the exact probability which we were expecting, and we have used the law of total probability here to get the required probability of getting a male student from all the classrooms here. So this is how we can use the law of total probability to get the total probability of a particular event given that we have given that we have the conditional probabilities already for that event on the other variable. So this is how we apply the law of total probability. Okay, so these were all the required basic concepts that one would want to cover in the probability theory. And next we'll be moving on to something called the expected values. So we'll be doing this topic in a different way. We'll be looking at a couple of questions here, which could be normally a little tricky, especially the second one here. And these are normally asked in some of the interviews based on probabilities theory. So we'll check how we can basically do these kind of questions here. So looking at the first question here, what is the expected number of tosses which are required for a fair coin to get the first head? Now the first thing here, since this is a fair coin, we know that the probability of getting a head and the probability of getting a tail in each of the tosses is 1/2 each. Now, since we want the expected number of tosses which are required to get the fair coin, to get the first head, what we do is, let's say we look at different cases. When can we get the first head? And if you remember, we defined a random variable in our first session. This was nothing but output of an experiment. Or better would be, let's say, a random experiment. Now this experiment is random since there are two possible outcomes and each has a particular probability, so we don't know what outcome will come, and therefore this is a random experiment here. Now the random variable here is actually defined as not what the output of the experiment here is, but the random variable x. This is defined as the total number of tosses required to get the first head. Now let us say we want to calculate this, the total number of tosses required to get the first head. Let this particular value be x, and since we have to calculate the expected value of x, an expected value is represented like ex, and the meaning of expected value is nothing but the average value of x. Expected value is nothing but average value of x. Now what are the possible various scenarios in which we can get the first head? Either we get it at, so let us say this is the outcome and this is the value of x. So if the first toss is head, we get the value of x as 1. Then there is a possibility that we get the first as tail and then head. So we only stop when we get a head, because that is what our aim is, to get the first head. In this case, the value of x is 2, since we require 2 tosses to get the first head. Then we can have TTH, 3, TH, 4, and so on. Now one thing to note here is expected value of x is always computed as the summation of value of x multiplied by the probability of x. So this is a very important concept which will be again and again used in probability and statistics, and therefore one should be very familiar with it. And actually it is very intuitive, since there are many values of x possible here. We can clearly see it could be 1, 2, 3 and so on, and we are just multiplying it with the probability of that x, and we are adding all these products to get the final expected value of the random variable x. Now let us say we make another column here, which is the probability of x. Now since this is a fair coin, the probability of getting the first head is nothing but 0.5. The probability of getting a tail and then a head is 0.5 multiplied by 0.5, because the probability of getting a tail is 0.5 and the probability of getting a head is 0.5. And since all the tosses are independent of each other, if you remember, for independent events, we can simply multiply the individual probabilities to get the joint probability, and that is what we did here, and therefore we get 0.5 square. Similarly, for TTH we'll have 0.5 Q, for TDTH we'll have 0.54 and so on. So the expected value is now calculated as 1 into 0.5 plus 2 into 0.5 square plus 3 into 0.5 cube plus so on. So this is like an infinite series for which we need to calculate the sum here. Now what we do is we multiply both the left hand side and right hand side by 0.5 to get 0.5 times the expected value as 0.5 square plus 2 into 0.5 cube plus 3 into 0.5 raised to power 4 plus till infinity. Now we simply subtract this particular second series from the first one. We get 0.5 EX. We are left with 0.5 plus 0.5 square. So 2 into 0.5 square minus 0.5 square is 0.5 square. Then 3 into 0.5 cube minus 2 into 0.5 cube is 0.5 cube, and so on till infinity. Now we cancel out 0.5 from both the sides and we get the expected value as 1 plus 0.5 plus 0.5 square plus 0.5 cube and so on. Now this is nothing but this is an sum of an infinite GP, that is a geometric progression, with first term as 1 and common ratio of 0.5. Since we are multiplying the each term from the previous term with 0.5, therefore the common ratio here is 0.5 and the first term is clearly 1. Now applying the probability, applying the formula for sum of an infinite GP, we know that the formula for sum of an infinite GP is nothing but A upon 1 minus R. So using this we get the required expected value as 1 divided by 1 minus 0.5, which is nothing but 1 by 0.5, which is 2. Therefore, the expected number of tosses required to get the first head from a fair coin is equal to 2. So this is how we can calculate the expected value using the very basic principle of using the formula for expected value itself here. Now moving on, we'll be looking at the second question here, which is what is the expected value of the number of tosses required to get the first pattern H, T and H. So we'll be looking at it slightly in a different way. So we'll be solving it in a different way so that you are also familiar with the second way of solving these things. So let us say we are looking at a pattern H, T, H here. Now let us say we assume the expected number of tosses required is X. Now let us say we already know that the previous toss was a tail. So if the previous toss was a tail, what is the expected number of tosses required now? So the expected number of tosses required would still be equal to X. This is because we still need first toss as H to start this particular pattern here. So we cannot really start it with T, and therefore we still need X more trials to get to this particular pattern which we had earlier decided. Now let us say we have our first toss as head. Then what is the expected number of tosses? Since we already have started this series here from H, now we only need TH. But it is possible that we can have H and then H. So this particular H gets wasted since we again have to start with this H as the first edge, and we would still need a t edge after this. So we assume that if we already have an edge here, we assume that y is the expected number of tosses required, given that we already have an edge, and therefore with HH we will still need a y expected number of tosses, since the first edge will get wasted here. Now let us say we get ht. Now since we already have ht, we only need h now. Now the thing here is, let us say the number of tosses required to get an h in this case is z. Now these are the only possible cases which we can have to get the required value of x. Now going in the reverse order, let's say we already have ht here. Now since we already have ht, we are calculating the value of z, which is the expected number of tosses required to get the next h, since we already have ht. Now let's say we have ht. Let's say we have ht. The next particular toss could be hth if we get a head, or it could be htt. Now if it's hth, then we already have got our pattern. So the probability of getting the next trial as head would be 0.5. Once we already have ht, there's a 0.5 probability that we will get the h in the next trial, and we already have our hth pattern. Therefore we would only need one more trial in this particular case, which is to get this particular head. But let us say there's a 0.5 probability of getting a tail as well. Now if we get htt, we'll have to again restart things, since we have to start from h. So again we'll have to restart things, and therefore we will need x more trials in this case. So this will become 1 plus x. This 1 is nothing but this extra trail which we got. So this is the tail which we got, due to which we had to restart counting. Okay, so now this could be written as z equal to 1 plus 0.5x. Now we have already looked at z. Now let us say we want to calculate the value of y. Y is when we already have an h, and the next could be either h if we get another h, or it could be ht. Now let us first look at hh. Since there's a 0.5 probability to get the next toss as h, and this will be counted as one trial since we are counting this h which we got here. But the problem here is, if we get an h, we again come back to this particular situation, because we still need a t after h, and therefore we'll need y more trials in this case. So if we get the second as h here, I'll repeat, if we get second as h after an h, we are back to this h situation here, and therefore we'll need y more trials in this case. But if we get a tail, we have ht, and for ht we already know we need z more trials, which we saw in this particular case here. So we can simply write it as 1 plus z. So this is 0.5 y equal to 1 plus 0.5 z. Now if we multiply the whole equation by 2, we get y equal to 2 plus z. So this is how we come to the value of y in terms of z here. Okay, now looking at, ultimately we have to calculate this particular value, which is the value of x. So let us say now we try to calculate the value of x. If we get first trial as h, we already know there are y more trials required, which we saw in this particular example here. So we can write it as 0.5 into 1 plus y. But let us say we get again a t. In case of t, we'll again have to restart, since we have to start from h, but we have got t here. So we'll again have to restart, and therefore we need x more trials in that particular case. So this can be written as 0.5x equal to 1 plus 0.5y. Now this can be written as x equal to 2 plus y, and y we already know is 2 plus z. This is 2 plus 2 plus z, so x become 4 plus z here. Now we already know z as 1 plus 0.5x, as we know from our first equation here. So we can write this as z equal to 1 plus 0.5x. So x equal to 5 plus 0.5x, which means 0.5x equal to 5 and x is equal to 10. So there are 10 expected number of trials required to get the pattern HTH in this particular case. So once again, like, you can go through this solution a couple of times, maybe the way I have explained it, and this could be a little tricky one, but yeah, this has been asked in a lot of interviews, and therefore it is an important concept which we wanted to cover in this particular session. So this is all from the basics of probability. We'll be moving towards probability distributions in our next session.